So our next speaker, John FEMINELLA, he works at Pivotal. He's here to talk to us about time and how it can often be implemented poorly in software. It's actually a really hard problem, so let's hear what John has to say.
Great. Thanks, Marcy. So I'm John FEMINELLA, and this is a matter of time. You can read more about me on the internet at two places where I have an internet presence. One is my blog that I use sporadically, and one is Twitter that I use much less seriously but much more frequently. So this talk is fundamentally a talk about assumptions, and I'd like to invite you during the course of the talk to think about what assumptions you might be making about time, specifically for this talk, but also more generally about software. So every time you write a line of code, you know, what assumptions are underpinning what you're writing? And I hope to make you think more broadly about that. So normally assumptions are great. We as humans operate in a world that is very confusing. And if we didn't have assumptions to guide kind of the basic ideas of how we would maneuver throughout the world, we might run into problems. So assumptions kind of ground us in what the default state for how we should behave is. And that's often a very reasonable way to operate. The problem is that sometimes our assumptions can get us into trouble, and I think this is particularly true with respect to software. So here's two different samples of a piece of Python code. On the left, we might say that pick two numbers, or pick two variables and assign to them the same number in Python. So here we'll pick 222, and then we ask if A is B, and it turns out that this is true. But if we do the same for 2222, if we add another 2 to the end of it, we get a totally different answer. So it seems like some kind of assumption has been violated. And in this case, it happens to be because this particular implementation of Python, CPython, caches small integer values, values in the range from -5 to 256, so that they're actually singletons. And then is measuring object identity and not value identity. So the fact that A is B is only true for those cached integers and not for the larger ones. Or maybe this one, hopefully none of you have ever written a method that looks like this, but let's say that you wanted to measure, you wanted to devise some kind of mechanism for determining if a particular year is a leap year or not. And we'll give it some value that is the year that we want. This will be an integer value, and we want to know, we want this method to tell us true or false in response to a given year. So pretty much everyone knows the first rule, that if you can divide the year by 4 and there's no remainder, then that's a leap year. So for example, 1996 was a leap year because 1996 divided by 4 goes evenly into 4. There's no remainder. But some people don't know about the fact that if a year ends with 2 zeros, if it's evenly divisible by 100, then it's not a leap year. So 1900, for example, was not a leap year. You might also think that 2000, by the same rule, was not a leap year. But it turns out that there's a third rule, which is that if a year is divisible by 100, but also by 400, then it is a leap year. So 1900 is not a leap year, but 2000 is a leap year. So that's how, that's a relatively simple rule that turns out to have a lot of tricky logic associated with it. And sometimes the rules that we want to encode into software aren't always about things that are straightforward. Here's some sociocultural assumptions that get encoded into software. In 2003, the Massachusetts Supreme Court ruled in a case called Goodridge versus Department of Health that same-sex marriages were legal. And that was great for the people of Massachusetts, but not so great for the people who had to update the database systems associated with keeping track of certain schemas around marriage. And this is an actual database schema from an actual piece of software that I worked on that needed to be updated. I mean, this has a lot of problems associated with it. So for example, it's hard to tell when people get divorced from this schema and things like that. But this is a sociocultural assumption being encoded into software, not a rule about when leap years occur or how often they happen and so on. So this talk, I think, is really a talk about people and the assumptions that we make and how those assumptions can lead us astray, particularly in areas that look like they're simple, but are actually quite complicated. And one of those areas is time. And I think time is actually very difficult because we made it that way. Time is not, I don't think, a fundamentally difficult idea. It just measures the passage of events between each other, but somehow we've managed to really screw it up. So first, to see if we can make it less complex, if we can untangle the spaghetti that we've introduced, let's talk about the basics of what time is and how we got to where we are now. So if we think fundamentally about what time is, it turns out the philosophers have been thinking about this for quite a long time, pun intended. And there are two basic schools of thought. One school of thought, the Newtonian school of thought, says that time is basically something that exists independently of whether humans exist or not. So if there are no humans, if there are no minds, time would still exist. The Immanuel Kant school of thought is sort of the opposite of that. He says that time is a mental construct the way that color is, right? Like, there's no reason to associate a particular wavelength of light with the color red or green or blue or whatever. That's just a perceptual quality that humans have interpreted wavelengths of light as. So Immanuel Kant thought that time was like that. For purposes of this talk, we're going to say that time is what stops everything from happening all at once. So just like space is what separates me from someone in the audience or me from the camera or me from the lights, time is what separates this moment and this slide from the next one. So now we come to a more difficult question. Having decided what time is, how do we decide how to represent it? And what are the ways that we might care about representing time? And what are the pitfalls and advantages of one representation over another? So to do that, we're going to have to think about the way that we represent time. And I want to invite you all to sort of go hop in your mental time machine and imagine that you're one of the first humans emerging from the muck and slime of history, and you've gradually accreted some kind of intelligence. And now you'd like to measure the passing of a season so that you know when to plant your crops, or so that you know how long it's been since you last ate, and so on. So to do that, we're going to have to develop some way of keeping track of time. And to do that, we have to think about some of the ways that we can keep track of time. So probably the most basic thing that you would notice as an early human is the fact that the sun rises and sets in the same pattern each day, or almost the same pattern each day. And we'll give that particular cycle a name, and we'll call that cycle a day. You might notice that there's a second cycle, which is that over the course of many days, the sun doesn't quite go back to the same spot in the sky after a certain amount of time each day. But eventually it does. And we can call that a year, and that's one revolution around the sun. So after a year, at the same point in the day, the sun will be exactly at the same point in the sky that it was a year ago. And then there's also the moon, which is another cycle. It's a little bit longer than a day, but shorter than a year. And when we see a full lunation, that's the moon going around the Earth once. So that happens about once every month, about once every 28 days-ish. So now we have these three cycles to start from. We call these cycles periods. And these periods will form the basis of our calendar structure. And one problem that we have right now, though, is that we can't measure anything more granular than a day. So what if we want to measure some kind of period that's inside of a day? How do we do that? Well, we can think of just putting a point somewhere on this continuum and saying that that's the point that we care about. So, for example, here we're measuring about a quarter of the way through day 182 on some arbitrary numerical system. But notice that how we represent that point is totally arbitrary. So we choose, as human beings living in the 21st century on the Gregorian calendar, we choose to represent that by dividing the day into 24 hours and saying that this represents 6 a.m. But somebody in the ancient Sumerian civilization might have said that that was the 5th night hour. So there are many different ways of representing that point, but it's totally arbitrary how you do it. There's no reason that one is necessarily more correct than another. So now we have this idea of time, which is picking a point, picking some representation of your period such that you can count them, and picking spots in that continuum. So now we have the idea of a calendar. If we have a way of measuring time, then we can map particular representations or points in that continuum to strings that we can use to communicate with each other. And the most basic way of doing this is to map days, that is like day 182 that we saw before, to a date, a string representation of the day. So in the Gregorian calendar, we number the days starting from a very specific date, January 1st, 4713 BCE, and then we go up from there. That's day 0, and then every subsequent day is one more than the previous one. So day 2,456,973 is November 10th of last year. But again, this is a totally arbitrary representation. If we choose to use the Game of Thrones universe as the basis for our calendar, we can come up with a totally different representation that maps days to some other completely different numerical string or a combination of numbers and words. So now we have this idea of calendar. We've got our time, and we've got a representation of time in the form of calendars. But what time actually is it at any given moment? How do we measure the passage of time? So I'd like to invite everyone to breach conference etiquette for a second and pull out your phone or look at your watch. And on the count of 3, I just want you to yell whatever time you currently think it is. So 1, 2, 3. Okay, so I heard most people say an hour and a minute, and a couple of people said PM. And I think I heard one person say business time, and kudos to you, sir. So most people said an hour and a minute, which is certainly one way of representing the time. But we can get more specific than that if we wanted to, right? We could add arbitrarily more specific units to that same representation. The problem is that when we do that, what are we actually talking about when we say it's 6:30? So let's go back to our time continuum. When we say it's 6:30, what we're saying is there's a particular moment in time, some point that we think it's 6:30 at. Except that's not really true. The statement, it's 6:30, refers to a range of values, not one particular spot. So the points where it's true, it's 6:30, represent a range of values. Everything from the moment it turns, the instant it turns 6:30 to right before it starts at 6:31. But if we be more specific, we don't escape this problem. We're only talking about a narrower interval, a narrower range of true values. So the problem we have is that moments are ambiguous. They don't actually identify a point. They identify a range of values. So we're looking for some way that makes it unambiguous, but being more specific doesn't help us. So, for example, here in the course of one day, it's true for 2 different ranges in the day that it's 6:30. So it's not like being more specific gets us anywhere. And those cycles repeat many more times. So every day we have those same 2 cycles. If we don't say AM or PM, we still have the ambiguity. And again, if we get more specific by just adding seconds and milliseconds, that also doesn't solve the problem. Now, the reason that this works for me as a human being, when you guys yelled out the hour and the minute, I know what time you're talking about. I know you're talking about today at Cascadia.js in the year 2015 at approximately 4:30 p.m. Because there's only one interval that would make sense to me as a human being in that context. I've effectively taken all the context that I have about today and recognized what time you're talking about. But we need more than that. We need specificity, not just granularity. We need a way of being specific about which of those many intervals we mean, not just getting the interval smaller. So the way that we can do that is to specify every single cycle, every single period that we had before in our representation of time. And if we don't have any more cycles, if we've uniquely identified each point in every cycle, then we have a unique representation of time. So instead of saying that it's 4 o'clock or 4:30, we have to say that it's 4 p.m. on a particular day with this date on this year in some calendar system. So seems like that gets us past the point where we have maybe this is the solution. Is that everything? Well, not really, because if you look at most software systems and you ask, for example, what today's date is, so here's JavaScript, and saying, let me give you a date and a time, and you give me some result, I get something that's not part of the representation that I specified before. None of those are part of the cycle. That GMT minus 0400 parentheses EDT, that doesn't appear anywhere in my input. So where did that come from? And more importantly, can other things go there? Because if they can, that means that we need to specify something that we didn't specify. So there's clearly something missing from our domain model that's making it a little off. We need something else that's going to go in that last spot. And that is what's going to give us the ability to represent times uniquely. So the crux of this issue is that we want times to correspond to a solar day. When it's 9 a.m. for you, no matter where you are in the world, the morning should more or less just be starting. So we want our morning times to be light times when the daylight is out, and we want evening times to be dark when the sun has gone down. So we want those times to be the same for everyone, no matter where they are in the world. The problem is that our Earth is round, and if we choose a universal time representation, at some points it will be dark for those people when it's 9 a.m., and it will be light for some people when it's 9 p.m. So a very clever man named Charles Dowd solved this problem in the US. He was a seminary teacher, and he was traveling on the railroads a lot. And he noticed that it was really frustrating when he would step off the railway platform and he'd maybe travel 50 miles, but the times at the different train stations would be totally different. So he proposed in the US the idea of standardizing on 4 different time zones. And that's how we wound up with the 4 different time zones today. This happened in the 1880s. So if we take Charles Dowd's idea and we have a common offset and we're just moving things according to that offset, we can solve a number of problems. So I live in Charlottesville, Virginia, which has an offset of UTC -4, and I have some friends in Maryland, New South Wales, Australia that are on the offset UTC +11. Now, we can communicate because we're using the same calendar, but not everybody is using the same calendar everywhere else in the world. So, for example, in Beijing, there are many times that use the civil Han calendar, while in Charlottesville, most times are using the Gregorian calendar. So, okay, if we all agree to adopt the same calendar, does that solve things? Well, not quite, because we're going to have to remember every time we switched calendars. Otherwise, old dates don't make any more sense. So, for example, in most of Europe, they switched from the Julian calendar in October 4th, 1582, to October 15th, 1582 in the Gregorian calendar. Not all the countries switched at the same time. Many countries switched over the course of several years, and that different provinces in those same countries switched over the course of several years. So there's a lot of ambiguity about what particular day it was, and you need to keep track of the days moving along. Another problem is that those offsets that we identified before, they also change over the course of a year. Maybe you've heard of daylight savings time. So, for example, in Charlottesville, we're on UTC -5 during the winter, but we're on UTC -4 during the summer. In Maryland, New South Wales, the same way. They're an hour behind in the winter and an hour ahead in the summer. But we can also change our offsets at different times in the year. So in Charlottesville, we change on the first Sunday in November and the second Sunday in March. But in Maryland, New South Wales, Australia, they change on the first Sunday in October and the first Sunday in April. And even worse, we've also changed our mind about when we're going to change those offsets. So we have those rules, but not all the time. And during different years, we had different rules. And Maryland, New South Wales has a totally different set of rules about when they change, and they change their minds at different times too. Another problem is that some of the times we'd like to talk about don't actually exist at all in a given time zone. So, for example, this time, 2:30 a.m. Pacific time on Sunday, March 9th, 2014. Seems like a more or less unremarkable time, but this actually occurs during a daylight savings time transition. So if I say, get me the U.S. Pacific time zone, and when I say convert that local time to a UTC time, it will turn out that there's no UTC time that matches that time. Because when we go from 2:01 a.m., at 2 o'clock a.m. on that date, we jump forward an hour to 3 o'clock a.m. So there are no times between 2 o'clock a.m. and 3 a.m. that exists in local time. So there's no UTC time that maps to that time. We have the opposite problem when you go back an hour in daylight savings. There, the same moment occurs twice, right? Because at 1 a.m., you experience all the times from 1 a.m. to 2 a.m., and then when the clock ticks to 2 a.m., you go back an hour, so you experience all the times at 1 a.m. again. So there's more than one UTC time that maps to that local time. So that's confusing. So there's clearly something missing in this relationship. We need some way of mapping calendars and times together, and we need a few more ideas in our domain model before we can make this work. So first is the idea of a reference time. So this is the UTC that we've all agreed on. We all have some central time that we're coordinating on. And then we have our local times. And then we have some way of measuring the difference between them. That's the time offset. So my time offset in Charlottesville, Virginia is UTC -4 right now. You guys in Pacific time are in UTC -7 and so on. And the way that we can represent time zones is by mapping every reference time, every point in that continuum, to an offset. And that's basically what a time zone is. It's a list of reference times and mapping them to offsets. And then you can just look up what your offset is at any point in that continuum. So that sounds really complicated. As we saw before, we're going to need to make a database to solve this. Fortunately, someone else has already done this for us. The Internet Assigned Numbers Authority, their job is to maintain a giant database of something called TZ data. And they have one time zone for every distinct list of historical offsets to remember. Every time someone changes their mind about when the time zones occur, when daylight savings times happen, what the offset is, and so on, that's a new time zone. So Pacific time, for example, we have a bunch of rules in TC data that say when Pacific time changed its mind about what time zone or what offset it was going to be in and when daylight savings rules applied. And you can see here in that very first row, it says Zone America Los Angeles. We switched from LMT, that's local mean time, to on 1883, November 18th, that's when Charles Dowd's rules went into effect. So we switched from local mean time to a -8 offset. The problem is that, again, a lot of different places have a lot of different ideas about what time zones should be. So in Indiana, there are at least 18 different time zones because different cities have adopted different rules about what daylight savings time means in the context of that city. It's possible to draw a straight line through Indiana and cross 11 different time zones, if you can believe that. So Indiana has a lot of trouble making up its mind. Fortunately, we don't have to do all this ourselves. There are libraries to take care of this, a lot of them. And in particular, JavaScript has the Moment.js library, which is pretty good. Java has something called JodaTime. .NET has something called NodaTime. Ruby and Python have their own fun little implementations that sort of work and sort of don't. But that's the missing piece here. We have this TC database that knows about the relationships between our calendars and our times. So now that we have that, how do we actually work with times? How do we use that representation to work with times in a software fashion? The most important aspect to capture here is that intention matters. These are all three very different ideas of what a time should be. So if I say, wake me up at 6 a.m., do you think 6 a.m. should change if I cross time zones? Or do I always want my alarm clock to wake me up at 6 a.m. every day, no matter what time zone I'm in? If I say that a call is on the 29th of every month, do you think that means the call is canceled in a February where it's not a leap year? If I say I want to go to the gym three times a week, do you think that means that those 3 points should be equidistant in time from each other? Should I be going to the gym at 12:47 on one day and then 4 in the morning on some other random day when I divide the week into 3 equal spaces? So there are different ways of representing time that we need to be aware of. The problem is that simple math usually doesn't give us the right answer. And that's because there are two very important distinctions to make. The first is duration. A duration is a concrete number of, it's a concrete representation of time that doesn't depend on what calendar you're using. Everybody knows how long 2,592 million seconds is. Or sorry, 2,592,000 seconds is. That's the length of about about 1 month. So the problem is that we also have a representation that is based on a calendar, and that's periods. And we can have a number of different representations of the same thing that are all equivalent. All of these are valid descriptions of 1 month. I can say 1 month. I can say 30 days. I can say 28 days if I'm talking about February. I can say 4 weeks if I'm counting weeks starting from Sunday. I can say 5 weeks if I mean weeks of any length. I can say 6 weeks if I mean weeks of any length that don't necessarily start on a Sunday, and so on. So some libraries handle this for us. Okay, here's Moment.js. Let's say we want to talk about the date January 30th. Okay, great, here we go. Let's say we want to go 2 months in the future from that date. Let's say we add 1 month twice to that date. We wind up with March 28th, which doesn't seem like it's 2 months after January 30th. It seems like it's 2 months minus 2 days. But if we add 2 months directly instead of 1 month twice, we get what seems to be the correct answer. Well, what happened here? What happened was that those operations weren't associative. When we added 1 month the first time, we went into February, and February only has 28 days. So the closest valid date we could get was February 28th. Then we added 1 more month, and we got March 28th. That's different than going from 2 months forward from January 30th. So those operations aren't associative. So we need to match times to our intention. We need to know whether we're talking about a duration, a period, or something else. Here's another example. Let's say I've got 3 dates, November 1st, 2nd, and 3rd. The reason a 10 is there is because JavaScript months start from 0. So 10 is actually the 11th month. It's not October, it's November. So on November 2nd, 2014, we have a DST transition. If we look at the number of milliseconds between the second date and the third date, we see that it's 90 million milliseconds. If we look at it from the second date to the first date, it's 86,400 milliseconds. So on the one hand, it seems like 1 day should be 90,000 seconds, but on the other hand, it seems like 1 day should be 86,400 seconds. If we use periods instead of durations, we'll get what seems to be the natural answer, that these dates are separated by 1 day. But what if we switch to time? What if we switch to a more specific representation of those times? So here I've got November 1st at 1 a.m., November 2nd at just before 1 a.m., and November 3rd at just before 1 a.m. If I ask for the difference in days between these two, it's 1 day between November 3rd and November 2nd, and it's also 1 day between November 3rd and November 1st. That's clearly not what we want. We probably wanted something that was closer to that. So our library is making an assumption that if we want, unless we have a whole day, we're not going to get 1 more day. So this is just 1 minute short of being a whole day. So that's the missing piece that we didn't have, the duration and period plus the time zone database. This gives us a complete representation of time. This is everything we need to make time work in software, and it's a matter of actually making that happen in our software representations. So in conclusion, I want to leave you guys with 3 thoughts. First, times are hard, and it's our fault because we really made it complicated by insisting on a lot of different rules about how things were represented. Second, our libraries can make assumptions that aren't necessarily the assumptions we want to make about how people use time and how we want to represent time. And third is that the intention that we represent in software is the most important thing for avoiding mistakes in terms of how we use time in software. So I'd like to thank the organizers, volunteers, and sponsors for making this a wonderful conference. There's a character in Futurama represented by God who says, if you do everything right, people won't be sure that you've done anything at all. And I think that's especially true about running a conference. So thanks very much, guys. I appreciate you showing up and staying for the very, very last talk of the day. And I hope you had a wonderful time at Cascadia JS.